Go ahead.
Okay. So today's speaker is Srilakshmi Jayaraman, and she's an independent postdoctoral researcher and a Newkirk Fellow here at HAO. She's been working with Wenbin Wang and also Astrid Mott, and she focuses on investigating ionospheric current distributions during magnetosphere-ionosphere coupling processes. Her academic journey includes earning a master's degree in physics from the National Institute of Technology, Calicut in India, and followed by the successful completion of her PhD in physics under the guidance of Professor Geeta Vichare from the Indian Institute of Geomagnetism and the University of Mumbai in India, which she received in February 2024. And during her PhD, she specialized in investigating quiet time ionospheric currents utilizing low Earth orbit satellites such as SWARM, COSMIC, and ICON, and complemented by numerical modeling frameworks including TIE, GCM, IRI, and the EEJ model. So please go ahead.
Thanks, Nick, and thanks, HAO, for giving me this opportunity to give a talk. So I will be presenting on topic of currents in the ionosphere, examining sources and their coupling with thermosphere. Some of the work done during my PhD and as a Newkirk Fellow here. So first, I would like to acknowledge my PhD advisor, Geeta, from Indian Institute of Geomagnetism, and then my Newkirk host, Astrid, and also other co-authors who worked in this project, like Art and Brian from UC Berkeley and Patrick from series. So in today's talk, I will be first introducing or giving a small introduction on the ionospheric currents, and then on the near Earth magnetic field measurements, because that's the way you estimate currents, is the convenient way. So then we will move on to the two topics which I worked on, which are like magnetic perturbations due to gravity and plasma pressure gradient currents, and why we need to study that and what we did in our work. And then another study is on effect of zonal wind shears on the equatorial electrojet sideband currents. So that will also be presented. So we all know that ionosphere is a ionized layer in the atmosphere. So there are many forces which act on this ionosphere, which can create currents. So these forces are mainly the geomagnetic field is there, and then the thermospheric winds push these ions and electrons in the presence of the Earth's magnetic field to create a quite time current system called the Solar SQ, which along with the neutral wind dynamics made divergence free along with the establishment of a global electric field. So here is a schematic where we can see the solar quiet currents, which are counterclockwise in direction in the northern hemisphere and clockwise in the southern hemisphere, and which has another component, which the main current is equatorial electrojet, which is an intense eastward current in the equatorial region. So these two can be expressed using the first two terms in the equation in a steady state ionosphere. So we can see that sigma is the conductivity, which is in a tensor, and so yeah. So this conductivity tensor has like why we represent it in tensor way, because in ionosphere the conductivity is anisotropic, and it has three components mainly, or we can say the conductivity varies in either parallel to the magnetic field, which is called the parallel conductivity, and then there is Pedersen and Hall conductivities, which are perpendicular to the magnetic field. So, and then this wind-driven current are proportional to the neutral wind dynamo, neutral neutral winds and the ambient magnetic field. Then there are two other smaller contributing currents, which are gravity driven and pressure gradient currents, which are represented using the expressions 3 and 4. We can see that the gravity driven current is proportional to the plasma density, and also on the, as we can see, any force acting on the plasma, like gravity or the pressure gradients, it will create currents perpendicular to the force and the ambient magnetic field. So that's what's shown here and here. So this pressure gradient currents are proportional to the pressure gradients and the ambient magnetic field, which in further is dependent on the electron density and ion and electron temperatures. So we will be focusing on these two currents first, but before that, study ionospheric currents, we need the convenient way, as I said, is to measure the magnetic fields using magnetometer. So we can place it in the ground or low Earth orbiting satellites, or using rockets. So the sources contributing to near Earth magnetic fields are either external to the Earth or to the internal to the Earth. The internal contribution is the main field, which we call can see at the fluid core, which is the main geomagnetic field, which contributes up to 60,000 nanotesla. And then there is crustal magnetization, which represents remnant magnetic fields in rocks and all. So those contributes in tens of nanoteslas. And then there are external fields, which are either ionospheric or magnetospheric contribution. So here we can see, as we mentioned, near to the equator, there is EJ, and then there are SQ in both hemispheres. Then there are other currents like gravity and pressure gradient currents also, and other currents like field aligned and interhemispheric field aligned currents are also present. We will not be going into these currents. We will be focusing on the quiet time and low to mid latitude currents. So here is a typical profile of magnetic field in the north direction from a SWAMP satellite. That's a low Earth orbiting satellite. So it shows like a higher magnitude since it's the northern component, magnitude in the equatorial region, and then it reduces to both hemispheres. So this is a typical profile where since it is a low Earth orbiting satellite, we can see that the local time or the longitude are mostly constant for the period we are considering, like in the low to mid latitude region. And it takes around 1.5 hours to cover one orbit. So in order to get the ionospheric currents from the magnetic field measured by a satellite, we need to delineate the effects due to other components. So that we do using any geomagnetic field model, like I have used HAOs, and what we obtain is called residual field. So this is during quiet time, we say that it is only due to the ionospheric current. So this will have components due to EJ, SQ, and the gravity and pressure gradient currents also. So here, if we look, it clearly shows a dip at the dip equator, which is an indication of the EJ, and then there is a large scale structure in the SQ. But it also has, as I mentioned, the other two smaller contributions due to gravity and pressure gradients. So why do we need to study this less intense gravity and plasma pressure gradient currents? First of all, these currents are in the region of the satellites which are measuring it. So satellites will be the only way to measure these, and they will only have the effect at this because of these currents. So in 2003, there was a paper by Lua which showed that they were the first time observations of the pressure gradient currents. So what they did was they assumed that any increase in plasma pressure should be counterbalanced by a decrease in magnetic pressure, and vice versa, and try to get a diamagnetic effect due to the plasma pressure gradient currents and obtain this expression, where it is proportional to the electron density, and then ion and electron temperatures, and inversely proportional to the magnetic field. So what they found using this assumption was that these the magnitudes of these plasma pressure gradient currents effects in magnetic field are of the same magnitude and spatial scales of those that due to crustal anomalies. So when you are studying crustal anomalies, you will need to correct for this magnetic perturbation due to plasma pressure gradients. So this is something they determined using the CHAMP satellite. So this is the EEJ profile, and further the this dashed ones represents the ones which are corrected after correcting for the magnetic perturbation due to pressure gradient current. So this is electron density variation, as we can see, since it should be perpendicular, proportional to the electron density. So they found that since this correction due to magnetic perturbation due to pressure gradient currents are in the same direction as that of the EEJ, so it can affect the sideband currents or any difference in the EEJ's profile. So this can lead to misinterpretation of EEJ. Further, following this paper, many researchers used this correction for pressure gradients in modeling or modeling like Earth's magnetic model, or and doing a secular variation model, or for a lithospheric magnetic field model. Also, it was used for determining currents in ionosphere, EEJ, and F-region currents. But in 2017, Mount and Richmond found that if we are only correcting for the plasma pressure gradient currents only, without considering the effect of gravity currents, it can cause a larger error. Why is it so? If we can look at this figure where the currents are plotted along the altitude, and blue is the gravity driven, and red is the pressure gradient current, which shows that in the below the electron density peak, we have pressure gradient currents in the eastward direction, and above it, it is in the westward direction because of the electron density gradients. And then there are gravity-driven currents which are peaking in the electron density peak near to that. So above this peak, we can see that this JG gravity-driven and pressure gradient currents, they tend to cancel. So if we were only neglecting the effect due to pressure gradient, or removing the effect due to pressure gradients, and do not consider this, it can lead to difference in which may not represent the true residual magnetic field, which we are using to, like we said, in modeling different magnetic fields or when obtaining these currents. So in our study, what we did was we tried to examine this magnetic field variations due to gravity and diamagnetic currents at LEO satellites altitude using observations. And then we also want to provide an estimate of these magnetic perturbations at these LEO altitudes. For that, what we used was cosmic satellite, which uses radio occultation techniques to obtain the altitudinal profile of electron density in the ionosphere. And so here it is like it's the polar LEO satellite around with an inclination of 72 degrees. So it is like around 6 satellites, and it gives around 1800 to 2000 occultation points in a day. So these are occultation points spread across the globe. So the color bars represents the local time. So what we want is, this is an example. This, yeah. So this is or satellite orbit pass of SWARM, which in the video, if you had seen, it showed that it as it is a LEO satellite, it always moves from pole to pole. So we need to have the occultation points or the electron density data in a latitudinal coverage. So if we look at this occultation points from cosmic, we can see that there is a good latitudinal coverage, but the local times of these points are varying differently. So we will be using some assumptions to take into account of the local time and get these currents in the latitudinal varying, because we want to correct for the low Earth orbiting satellites magnetic field measurements. So yeah, and other things we taken from the ion and electron temperatures were taken from International Reference Ionosphere model, and then the CHAOS model was used to obtain the ambient magnetic field. So what we did was to get the magnetic perturbation due to gravity-driven current along the magnetic field. We use this expression given by Mout and Richmond, which integrates the gravity-driven current from the height of interest to the topside ionosphere, and the same is done for the pressure gradient currents too. So here we can see that gravity, as I mentioned earlier, also gravity-driven currents are proportional to the electron density, and then when we integrate it, the effect will be different in. Yeah. Sorry.
Yeah, quick question. So in that formula, the JG, is that N just the plasma density in the ionosphere?
Yes.
And also the B is assumed is the IGIF is a fixed value?
Yeah, I'm using CHAOS. Yeah, it is fixed. Yeah, it varies with altitude.
Yeah, but it does not vary with time, does it?
No, it varies with time.
Also vary with time.
Yes.
So that's like a separate model. It's not like from ITCN, the magnetic field.
No, CHAOS is a model which uses the satellite data and the ground measurements or all the magnetic field measurements, and they combine it and use spherical harmonic analysis to give magnetic field measurements due to magnetosphere and this core and crustal fields.
But back to the density again. Where is the density from?
Density is from cosmic.
Cosmic. Oh, sorry. I was thinking about the models. Thank you for clarifying.
Yeah. So, like I said, we need to get the latitudinal coverage of the plasma density. So for that, first, what we did was, we do not consider the day-to-day variability. So we mixed up days at fixed longitude and local time. Then another way was to mix all the longitudes on a given day and local time. So with the first way, where we fix the longitude at a given local time and high solar flux, this is the electron density profile obtained from the cosmic satellite. So it shows like starting to show like an equatorial ionization peak with two peaks. It's still not separated. And so because of this electron density, what are the currents and magnetic fields? That's shown here. This is due to gravity current, and this is due to plasma pressure, and this is the combined effect. And then there is magnetic perturbations due to gravity, pressure gradients, and then their combined effect. So we can see that as the equations suggested, the gravity-driven currents are directly proportional and moving. It shows the eastward currents in the ionosphere and have a peak near the electron density peak. Then there is pressure gradient currents, as we say. Below the electron density peak, we have like eastward currents, and above it is westward currents, which when combined together, we obtain an eastward currents in the ionosphere with the peak in the lower altitude, and it reduces as we move towards higher altitudes. And if we are to look at the magnetic field perturbations due to this gravity, we see that it is along the magnetic, and so we are showing the magnetic field perturbation along the ambient magnetic field. So this is a northward perturbation, and because of pressure gradients, we have southward perturbations, which when again combined gives something which is shows northward magnetic perturbations in the lower altitudes, and it reduces as we move towards the topside ionosphere. Now, when we look at these variation of magnetic field to these currents with solar flux, what we did was separate out these with respect to latitude. So this is equatorial region, and then there is southern hemisphere and northern hemisphere. So we have divided it into 5-degree bins, and then increase the bin size as we moved away from the equator. So the red shows the magnetic perturbation due to gravity, and blue is due to pressure gradients, and green is the sum of it. So from all these figures, it can clearly see that as the solar flux is increasing, the pressure gradient is increasing, and also the gravity is also increasing, and then their sum is also increasing. But as we move away from the equator, its magnitude is reducing, and it almost becomes 0.5 or very small at these mid-latitude regions. Yeah. So now, if we go to look at the estimate these currents and magnetic perturbation in the second way, where we fixed the day and mixed up the longitude. So you should note that here we are plotting with respect to dip latitude. Earlier it was with respect to geographic latitude, since we mixed the longitudes. So here is the plot of electron density, which shows clear equatorial ionization anomaly peak with the 2 distinct peaks in the ionosphere, and which is again seen in the gravity-driven currents, and which shows eastward currents. And like earlier, we can see the westward currents due to pressure gradients in the upper ionosphere, and in the lower ionosphere we have like eastward currents. So these further produce that southward magnetic perturbations in the diamagnetic effects, and northward in the gravity driven. So this combined effect again gives, like in the equatorial to low latitude region, it is around 6 to 8 nanotesla, and as we move up, it reduces, and in the low Earth orbiting or LEO satellite altitude, where SWAM is 450 kilometer, it is around 2 nanotesla. So since we combine the longitudes, we also want to see the limitation of this study, which is like effects due to longitude, which can be coming through the 1/b factor coming in the gravity-driven and pressure gradient currents expressions we saw earlier. So here is what we plotted with 1/b with respect to geographic longitude and latitudes. So there, if we look at the 300-degree east longitude and at 100, 120, there is a difference of around 15,000 Tesla inverse difference. And if we are to look at only at one longitude and then look at it, it also shows a strong asymmetry about the dip equator. So there is a strong dependence on longitude. So as which longitudes are coming, or we are choosing, or the occultation points cosmic, so at 15 LT, the result may vary differently. But the in qualitatively, the effect will be the like higher magnitudes or in the lower altitudes, and it reduces as we move up in the ionosphere. So then what we did was we tried to compare it with the diamagnetic approximation, which was given by Luer's paper. So here are the results from our study at 15 and 20 LT, the magnetic perturbation due to pressure gradient and gravity-driven currents, and then what we obtained from their approximation for diamagnetic currents. So we can clearly see a difference in direction itself. It is northward in when we combine the gravity and pressure gradients, but only if we look at the diamagnetic approximation, it is in the southward directions, and also in the pattern where it is higher in the lower altitudes, and it reduces as we move up. that's not seen here, which shows like a different pattern with two different kinds of peaks near to the electron density peak. So when we look at the difference between these two, it produces around 7 to 8 nanotesla near to the equator at 250 kilometers altitude at 15 LT, and for 20 LT, it gives around a difference of 4 to 5 nanotesla. So this correction based on diamantic approximation, if we only consider that, it's not good. And if we should be correcting either both gravity-driven or pressure gradient currents as suggested by the model simulations from Mount enrichment, we also could get to the same conclusion using the observational data. So, but we also want to provide an estimate of these quantities. So for that, we found that there are some limitations for the observational data, like we had to mix the longitudes or the day-to-day variability to obtain this, and also the induced, these currents have an induced electric fields in the E region, which again produces currents and thus contributes to the magnetic fields. So that is not considered in the observational data. So that can be done using modeling only. So we again go back to model to give an estimate of these fields so that researchers from who you want to use magnetic field data from LEO satellites can know whether we have to correct for it or not according to their local time choice. So using TGCM, we obtain the magnetic perturbation due to gravity and plasma pressure gradient currents. So here is it. So this is what we compare with what we obtain using observations. So it is qualitatively showing something similar, but we have higher magnetic fields in the lower ionosphere, and it reduces as we move up. But there are some features which we cannot obtain using observations. That's because these southward magnetic fields are caused by the induced electric fields due to these currents, which can obtain only using the model simulation. So, and also to look at the longitudinal variability, we plotted the effect from gravity and pressure gradients with respect to longitude, and we found that as we expect, since the magnetic field, it is varying with 1 by b. So since the magnetic field is low near to 300 degrees east longitude, it showed more magnitude at this longitude. So we will be focusing on these longitudes only. So here are the local time and seasonal pattern of these magnetic perturbations due to gravity and pressure gradients at 300 degrees east longitudes and different altitudes and for seasons. So here are the altitudes, which are 350, 425, and 550 kilometers, which are again shown in March, June, September, and December solstice. So at the lower altitudes, we can clearly see a peak near to the equator. And as we move away from the equator, it is reducing. This is around 8 nanotesla it's going to 0, and then there are small negative or southward magnetic perturbations of -1 nanotesla in the mid latitudes. As we move higher up in altitudes, we see that this peak near to the tip equator is vanishing, and we can see two southward magnetic fields at lower latitudes of 2 to 3 nanotesla at altitudes of 550 kilometers. So that means even at 550 kilometer altitudes, we have a contribution due to this superposition of gravity and pressure gradient currents. So, and also we can see from this figure that March equinox and September equinox, which show higher magnitudes compared to the June and December solstice. So this was to show, give an estimate like for the contribution due to gravity and pressure gradients. It is prominent in the daytime from 12 to 18 local time, as we can see here, at 300 degrees longitude and high solar flux with a magnitude of can give up to 8 nanotesla. And now we move on to our next study, which is on the effect of zonal wind shears on the low latitude EEJ sideband currents. So as I mentioned earlier, equatorial electrojets are intense eastward currents flowing along the dip equator in the ionospheric E region day side, on the day side. So this is a typical profile we obtained from a LEO satellite, which shows eastward currents at the dip equator, and as we move away from the equator, it reduces. But near to plus or minus 5 degrees or so in the below plus or minus 10 degrees, we can see that there are westward currents. So these currents we call as sideband currents. So why we need to study the effect of these zonal wind shears on the sideband currents. So there was a study by Famitakoe et al. In 1976, which used the Richmond's physical model of EEJ to show that increasingly westward winds. So I can show you. So increasingly, these are the wind profiles in ionosphere from about westward winds from 135 kilometers to around 180 kilometers, and then it is constant. So these winds, so these are the conductivities, Hall and Pedersen conductivities in the ionosphere. Then these winds create these westward sidebands. That's what they're shown using model. So if we can see, so these in ionosphere we combine the effects due to winds and also due to electric field. So this E profile shows the effect only due to electric field, which shows EJ kind of peak in the dip equator, and it reduces as we expect. It does not consider the effect of winds, and only due to winds we have a profile like F, which is shown here. When we combine the effect due to winds and electric fields, we obtain something like this in the as shown in the figure 3. So this shows a westward sideband currents, and this they attributed to the gradient in zonal wind at these altitudes from 130 to 180 kilometers. So that's what we are trying to achieve using observations. For that, after 50 years, we had ICON, the satellite, which gave zonal wind measurements, and the simultaneous measurements of EJ was also, equatorial electrojet was also there from the SWAM satellite. So how does the vertical shear of zonal winds affect the westward currents at low latitudes? For that, we used as I said, ICON satellite, which was an equatorial satellite at an inclination of 27 degrees, which provides the neutral wind vector data by from this instrument called MIGHTY. And then there is SWAM satellite, which provides the equatorial electrojet data, which was inverted from the magnetic field measurements from the satellite. Then, so here is what we do. So the ICON is moving from along the longitudes from westward longitude, west longitudes to eastward, and at the same time, SWAM is moving from pole to pole. So we need to find conjunctions where both these satellites are present. So for that, we looked up at the daytime where from solar local time where it's where within 9 and 15, and then their time differences should be within half an hour, and longitudinal difference should be within plus or minus 10 degrees. And also the wind measurements where should be in the equatorial region. So that's how we found conjunctions between these two satellites. For the period we considered, it was from 2020 to 2022, and in 2020 to starting. So the solar flux was very low, and only for this period we had solar flux above 100. So there was not much of an effect of solar flux, and then we restricted the data for Kp less than or equal to 3 plus. And so these are the conjunctions which we obtained from SWAM A or C with ICON, and the colors represents the local time. And then there was these are the conjunctions we obtained from SWAM B and ICON. So yeah, for after that, what we did was we tried to categorize this data conjunctions we obtained based on the intensity of the currents, like high, medium, and low, based on their intensities. If the current is less than -30, then it's high, then -30 to -5, it was medium, and it was low if it is greater than -5. So that is shown using different symbols in C1, C2, and C3 here, so for different conjunctions with ICON. So with this, what we see is that we do not have enough data to be distributed into longitude and seasons. So we are neglecting the effects due to these components, longitudinal variability and seasonal variability. And once we obtained these conjunctions for category 1, 2, and 3, what we did was we tried to do a Monte Carlo analysis using all the data obtained and found the mean for SWAM and ICON, SWAM's equatorial electrojets and the ICON's winds. As you can see, from when the currents are smaller and the gradient in zonal winds are smaller, and as the gradients are increasing, the currents of the sideband currents are also increasing. So that's what we obtained from SWAM A and ICON, and then further we obtained the same from consistent results from SWAM B and C. So this, when we plotted, or we further categorized, first we showed only 3 categories, then we further categorized into 5, and then plotted for SWAM A, B, and C with gradient and the sideband currents, we obtained a linear connection kind of with a correlation coefficient of 0.93, which then we used these winds obtained from ICON in Richmond's EEJ model and obtained a similar pattern with the correlation coefficient of 0.98, even though with a smaller magnitude. So with these observations, we obtained that a persistent zonal wind change, that's the slope of this graph, which gave -24 milliampere per meter for an increase of -1 meter per second kilometer gradient change in zonal wind. Yeah. So yeah, in short, for this presentation I presented, it is that we do not need to correct for gravity and pressure gradient currents if the LEO satellite, low Earth orbiting satellite, is above 700 kilometer, or if the satellite traverses during period of low solar flux. But since we are approaching the high solar, we already in the high solar flux region, so these contributions will be high, and we will need to correct for these climatic perturbations in the coming years. So it is prominent in the daytime from 12 to 18 LT at 300 degrees longitude and high solar flux with a magnitude of 8 nanotesla at around 350 kilometer. And then this study is the first time observational evidence connecting the zonal wind shears with the low latitude sideband currents. So increase in also that we found that increase in zonal wind shears in Pedersen region increases the EJ sideband currents. Yeah, thank you. And any questions?
Okay, are there any questions? Yeah.
Yeah, kind of a basic question, but are these currents for the sum of the currents required to be divergence free?
Yes.
So nothing gets diverted into a gill line current.
Oh, it is. I can show you a figure. Yes. So this is how pressure gradient currents flow. So this is a high pressure region, and these are low pressure regions. So they move along a constant pressure line, And since the magnetic fields are magnetic field is reducing, so the westward currents in the upper ionosphere will be more than the eastward currents flowing here. So they will be flowing through the field line currents and producing eastward induced electric fields, and then further in the dusk side again move up and close. So that's how they close and becomes divergence free. So like that for the gravity currents.
But, okay, so this is, you're looking here at gravity plus pressure. And the other currents in they're flowing like Pearson, Hall, etc. Those combine to stay divergence free in this region.
Yes.
Okay. Just a little bit. So do you actually test for that when you're analyzing the data, or is it an assumption that it's satisfied?
No, I haven't tested. I think Art and Astrid might have tested it.
Okay,
It's from their paper. I haven't tested.
thank you.
I have a quick question. So interested in the ground magnetic perturbation state of those in the atmosphere. Just curious for the gravity or the plasma pressure related atmospheric current. I presume their contribution to the ground perturbation would be very minimum, right?
No, they do not contribute in the ground. Yeah, because they close in the ionosphere
okay.
itself, so it will not
So it
contribute.
only affect those atmospheric.
Yeah, this it will be contributing only to the LEO satellites. So that's why we need to correct only for not for the ground.
Also, another question. So, yeah, I'm also interested in the EVG data set you mentioned from Swan satellite. So I guess it's publicly available.
Yes,
So
yes.
what's the temporary resolution of the data product?
It's like 1 second.
Okay, 1 second.
Yeah.
Okay.
Sorry, 1 minute.
Oh, sorry.
It's
Sorry, 1 minute. Okay. Thank you.
Yeah, I have a question. So how does this magnetic field perturbation, the magnitude, you said it's like 8 nanotesla. How does it compare to the magnetic field perturbation that is during a solar flare, for example?
I
Haven't looked at the
Looked
solar
at it.
flare. Yeah, because I remember the solar flare can also changes the EEJ sometimes.
It
can't
is
see.
not depending on the conductivity only so how the electron density is varying with solar flare, so these currents will also vary. That's all I can comment, but I'm not
Okay.
sure how much it will vary.
The magnitude compares. Okay.
Yeah.
Okay.
The EST effect, the room current, which is significant. So have you backed off of that out of this, or is it?
Yes, so we are using HAO's model, which models this DST using ring current index. So we are using that. Okay, it accounts for the symmetric ring current, but not for the asymmetric, I guess. But yeah, for
I have another question. So why do you use Kale's model in terms of, as versus to the IGRF?
SWF only gives the geomagnetic, main field, right?
Yes.
Yeah, but the Kairos gives crystal, and it divides into crystal and also the magnetospheric field also.
I see. Is this correction be able to implement it in TREGCN?
I think it is there, but yeah,
Or it is already?
yeah, it's in the 3D dynamo.
Oh, okay.
It is there, but it's
I guess
it's always keep it. I think, yeah, do not use it.
maybe it is in the total. Maybe it's in the current density that is from the TIGCM, but we don't separate them out. Maybe we don't look at them separately.
I think the gravity and pressure gradient currents, they are not looked up at all. It's not in the currents. You have to give. I'm not fully sure how to say that. Yeah, it's not in the currents which is given from the TAGCM, but you have to calculate it separately, I think, in the model itself.
Okay, I see.
Either I can commit.
Yeah, in a previous plot, you showed the gravity-driven current. That's mostly at like a 300-kilometer altitude.
Yeah, from 200 to in the F region mostly.
Yeah. So what do you think is the most important parameter that determines that the altitude and the distribution?
The electron density.
Density.
Yeah.
Okay.
So it is it depending on the like in the expression shown, it is directly proportional to the electron density.
Yeah, I guess. Yeah. So what you found from the analysis is like between local time 12 and 18. That's the most important. That is from this gravity and the plasma pressure. So this means that during the pre-reversal enhancement, this may not be that important. During pre-reversal, that would be after 18 o'clock local time.
Important, but the magnet, we compare only with, it is showing a peak from 12 to 18.
Yeah.
Yeah. But during pre-reversal enhancement also, it has some component.
Okay.
Yeah, but it will be
Smaller, okay,
Smaller.
compared to this period.
Yeah.
Okay.
Any questions from anyone online? Yes.
Yeah, I guess I still have that question about pre-reversal enhancement. I remember I read the Rod Hillis' paper, and he was talking about why there's like what happens during pre-reversal enhancement, and he has this figure, and then it's talk about it's like a gravity, because of gravity, G that is kind of is important to pre-reversal enhancement. Electric field. So I didn't understand that when I read that paper. That's why I asked this question. So, yeah, it's just a comments. I still don't understand. I don't know if the gravity wave is important. But G is important. I'm not gravity wave if G is important for the pre-reversal enhancement. Yeah.
Seems like no more questions. So thank you again.